Welcome to the fourth presentation on drill string and drilling dynamics, which is devoted to the low frequency behaviour of the fluid system. Other presentations look at the interaction of the fluid with the rest of the system. The fifth talk on motors and the sixth on control, and the seventh talk is on how sound propagates through the borehole fluids. First, an outline of what's in this presentation. We will have a recap of what was in the first presentation on a good low-frequency model of the system, looking at the dynamics of small variations, and the important point that it takes a long time before what happens at the bit to be seen at the surface. Then I will look at the full nonlinear system and show you what happens to downhole flow when the pump flow changes a lot, for instance, when the pumps are started or stopped. Finally, I will show you how to reach a stable downhole flow a lot faster. Before thinking about large variations, let's go back to small variations. This is a repeat from the first presentation. Fluid sound speeds are a lot lower than those in steel, so in a typical borehole it takes seconds for the first effects of what is happening downhole to reach the surface. Fluid sound speeds also vary significantly from one well to another due to different fluid compositions. And for oil-based mud, they could also vary significantly along the well. However, as there are not sudden transitions, it is not too bad an approximation to use the averaged properties. Just like the axial system, at low enough frequencies, the fluid acts as a spring. However, whereas in the axial system, for the same length, the system looks stiffer as the metal cross-section increases, for the fluid it becomes more compliant. It's a volume effect. Oil-based mud is significantly more compliant, less stiff than water-based mud. So at late times, low enough frequencies, there is a simple compliance condition linking the surface and downhole flows and the rate of change of pressure. At the bit, there is a pressure drop that is quadratic in flow, not linear. In reality, there is a distributed pressure drop along the pipe too, which we shall get onto. But the main features of the system come out with just a pressure drop at the bit. For small variations, we can linearize and end up with a very similar equation to that for the axial system. The fluid system acts as a low-pass, one-pole filter. The time constant depends on the fluid type, but as there is no equivalent of the rock drillability, it does not change suddenly. The system is actually non-linear, so for a given drill string and set of bit nozzles, the time constant grows linearly with the mean flow. So what happens if there is an acoustic source, a source of pressure variations, near the bit? We assume that the surface flow rate remains constant and solve for the change in downhole flow rate and the pressure. With constant surface flow rate, if there is a pressure change, then from the first equation, the flow rate through the bit must change, and then from the second equation, that further changes the pressure. So if there is a pressure increase near the bit, the flow through the bit has to go down. If the bit flow rate goes down, the pressure drop across the bit goes down. So the total pressure increase seen above the acoustic source and the bit is less than the increase in pressure drop across the source. Unsurprisingly, the same low-pass filter equation applies. So the pressure seen above the whole source bit system is a low-pass filtered version of the pressure drop across the source. We'll get onto motors in more detail in the next presentation, but this has important implications for interpreting what the motor is doing. To a good approximation, the pressure drop across a downhole motor is proportional to the torque on the bit. This is synthetic data that shows what you would see at the surface, but you will see the same features in real data. The top panel shows the torque, the bottom panel the surface pressure, both as measured with normal sensors at the surface. One feature stands out, that the torque trace has much wider frequency content than the pressure. But let's put the two traces together and rescale to compare. As well as a reduced frequency content, there is a delay between the torque and the pressure. The pressure is significantly behind the torque. Both these effects come from the one-pole low-pass filter. The low-pass filter both reduces the frequency content and introduces a delay. An obvious interpretation of reduced frequency content and a delay between the two channels will be that it is a wave propagation effect. The fluid wave is slower, so there is a delay between when the two signals reach the surface, and it is also attenuated more by viscous drag. It is true that the fluid wave is both slower and more attenuated, but that does not account for the delay observed, or the observed difference in frequency content. At these frequencies, it is from the combination of a compliant fluid and a bit pressure drop. But of course, there can be large flow rate variations. Every time there is a connection, the pumps are switched off and on again. Also, a common method for downlinking to downhole tools is through variations in flow rate, which have to be a significant fraction of the mean value to enable reliable data transmission. This is the simplest equation we would like to solve properly for a prescribed surface flow rate, the simplified model with all the pressure drop at the bit. Solving the nonlinear equation for general flow rates is not possible analytically, but if the flow rate is just changed suddenly from one constant value to another, it can be solved quite easily. We assume that the system is initially in a steady state, with flow rate q bit 0 at surface and downhole, and then at time 0, the surface flow rate is changed to q surface, and we solve for q bit. If the system were linear, then the change in flow rate would be proportional to an exponential in time, or equivalently, the time would be proportional to a logarithm of the scaled change in flow rate. When we solve the nonlinear equation, we get a first term, which is that time is proportional to a scaled logarithm, but there is an additional linear term. The most important consequence of this is that if the surface flow rate is dropped to 0, such as when the pumps are switched off, the bit flow rate drops linearly to 0. Of course, what we monitor at the surface is the pressure, and this is quadratic in bit flow rate, so the surface pressure drops in a parabola. In reality, it doesn't quite go smoothly down to 0, as at some point the flow rate through the nozzles is low enough that the flow goes from turbulent to laminar, and the last bit of pressure disappears all at once, but that's only right at the end. Turning the pumps on is a bit different, as both the logarithmic and linear terms are non-zero. And here is the solution comparing pumps off and pumps on, looking at flow rate through the bit, assuming that all the pressure drop is at the bit. The time is normalized to the time it takes for the flow rate to drop to 0 for pumps off, which is the characteristic time of the system. Interestingly, you can see that on pumps on, the flow takes several times the pumps off time to stabilize. After one pumps off time, it is only at about 85% of the steady state flow rate. This has consequences for starting up acoustic-based telemetry systems, as we will see soon. This is for a very simplified system, but for very long wells, most of the pressure drop is along the pipe, so it's not obvious that this model fits for long wells, but qualitatively, not much changes. Solving the real system numerically, the simplest way to model the distributed pressure drop is to approximate it as a succession of pressure drops along the pipe, with no pressure drop between them. As the model is nonlinear, it can be a bit unstable if parameter sizes vary too much, so it's best not to divide the pipe up into too many sections, so that each of the discrete pressure drops is of a similar size to the bit pressure drop. The other simplifying approximation is to assume there is a constant pressure gradient along the pipe, and while general analytic approximations are not possible, it is still possible to calculate what happens when the pumps are turned off using a power series. When we do this for pumps off, the effect is to have a relatively short delay before the system asymptotes to a linear drop in flow rate with time. Some equations that describe this are in US Patent 8196678. So what about startup? This is for a 3 pressure drop model where the pressure drop along the pipe is the same as the bit pressure drop. I plotted the flow rate at the surface in black, and then along the pipe at 1/3 of the way down, 2/3, and at the bit. Everything looks quite well behaved as you go down the pipe. The flow rate is progressively more damped. The timescale here is normalized, just as before, the time it takes for the flow rate to drop to 0 when the pumps are turned off. Comparing the pressure measured at surface with the bit pressure drop, they are qualitatively very similar. The most important parameter in the fluid system is the hydraulic time constant. It depends on something that is quite difficult to calculate, namely the average fluid compliance. Luckily, it can be estimated quite well from the data. Looking at the time to zero on pumps off is very error-prone. The gradient of the pressure curve is very shallow as it approaches zero, and then the fluid flow goes non-turbulent, or some rig activity will perturb the system. If you look at system startup, in turning the pumps up to full flow in one step, then the time the pressure takes to reach 70% of its final value is a good estimator. Also, this time scales with flow rate, so if you have a good estimate and change the mean flow rate by a known proportion, then the time constant will change by the same proportion. Sometimes the flow rate at startup is increased incrementally, in which case this method will not work. Rather than look at time to zero at pumps off, it is more accurate to look at the time for the pressure to drop to 1/4 of its steady state value, implying the flow rate has dropped by a factor of 2, and then double for the time constant. This is not so accurate when the pressure drop is distributed as the startup method. As we have seen, it can take several hydraulic constant times for the downhole flow rate to stabilize. For a system with a time constant of 15 seconds, this is less than a minute, but in long wells with big pipe and oil-based mud, the time constant can be over a minute, so the stabilization time is several minutes. Acoustic measurement while drilling systems require stable flow to reliably initiate communication, so this can be a considerable problem. Can we get the system to start up and stabilize faster? The answer, of course, is yes. Fast startup takes the pumps initially to a higher level, then drops them down to the steady state flow rate. The reason for the slow rise in downhole flow rate is that fluid compliance requires more fluid to be pumped in initially than emerges through the bit nozzles. If we can get that fluid into the system quicker, the downhole flow rate will be stabilized faster. The worry that many people have is that the system will blow up. The surface pressure will go too high and it risks the pop-off valves blowing and rig safety. This is not so. The only point of doing this is when the hydraulic time is long, and whatever you do, the pressure rises slowly. In fact, all you have to do is keep an eye on the surface pressure and bring the pump flow rate down to the final value when the pressure hits a threshold. For instance, what you expect it to be at the final flow rate when the flow has stabilized. Something automated would of course also work more reliably. It means that MWD telemetry can be stabilized much faster, and this has been successfully tested on a long well in the North Sea. The same methods can be applied to produce more precise transitions using flow variation downlink, though this would have to be automated. Let's look at what this means. This is the same system we looked at before, with the same pressure drop along the pipe as at the bit. At startup, the flow rate is initially taken up to a bit over 20% above the final flow rate, and then brought down. You can see that the downhole flow reaches very close to its final value, just over 1 hydraulic time constant time after startup. With normal startup, this would take several hydraulic times. However, you can see that 1/3 of the way along the pipe, the flow rate does go significantly higher than the final bit flow rate. What does this mean for the surface pressure? With this length of high flow rate, the pressure just creeps above the final equilibrium rate by the time the flow rate is brought down to its final value. In fact, this can be used as the criterion for dropping the flow rate to its final value. I've already mentioned one patent, so it will not surprise you to learn that there are patents on this work. However, for startup you may be in the clear, at least in the US. Obviously, if you want to do this, you need to check what applies in your jurisdiction. There was a US patent application, but it was abandoned. For improved downlinking, there is a US patent, but so far as I can tell, not elsewhere. Check with your lawyers first. And no, although there is Schlumberger IP and it has been shown to work for both startups and downlinks, it has never been commercialized. So to summarize, the hydraulic system looks like a nonlinear, low-pass filter. For small changes, it is nearly linear, and the time constant is the pump's off time. This is a function of both the volume and type of fluid, and the pressure drop at the bit and along the pipe. The time constant is from seconds to minutes. When the pumps go off, the bit flow rate drops near linearly. That is why it takes time for the surface pressure to drop. At pumps on, it takes much longer for the bit flow rate to stabilize. This 85% of flow is the 75% of the pressure rise rule I told you about, converted to flow. Finally, improved startups and flow rate changes are possible through applying this theory. We are not done with fluids by any means. Presentation 5 is all about motor theory. Presentation 6 includes auto drillers controlling our pressure, and Presentation 7 looks at fluid acoustics. Comments, questions, etc. to the email on the bottom right.